Welcome viewers to the sixth lecture for the online series of lectures for the course of Algebraic Topology 2. The goal of this lecture will be to state the Eilenberg-Steenrod axioms and then show that simplicial homology theory obeys these axioms. The Eilenberg-Steenrod axioms. All right. So in order to establish this axiomatic approach, we need a few ingredients. So let us try to introduce those ingredients by means of definitions. Here goes the first definition, which introduces the objects of a certain category that we are going to work on. Okay, let A, calligraphic A, be a class of pairs x comma A of topological spaces with A being a subspace of the topological space X such that the following conditions are met. First one, if the pair x comma A belongs to the class calligraphic A, then so do x comma x, x comma empty space, A comma A, and A comma empty space. All right. The second condition tells us that if x comma A belongs to this class calligraphic A, then so does this pair x cross I comma A cross I. Note here that given topological space X and its subspace A, X cross I and A cross I are topological spaces in the usual sense in product topology, and A cross I is a subspace of X cross I. Okay. Thirdly, there is a one-point space P such that P comma the empty space is in the class A. We shall call A an admissible class of spaces or pairs of spaces, if you like, for a homology theory. Okay, so what we have is the class of objects here of a category. So we are going to call it admissible category. So the objects here are these pairs of topological spaces satisfying these three properties, but we know from the concept of category that we also need morphisms that do the talking between the objects of a category. So now we need to describe those morphisms, all right, or functions between objects if we think in terms of sets. Okay, so let's do that. Now our second definition is about the morphisms of the underlying category. Definition. All right. So here is something I should tell, that we are following the book by Moncrief, and until now, even in my notes, I am not mentioning the category explicitly in the notes as well. But this is essentially what we are doing. So we are trying to understand the category of this admissible class of pairs, okay, where the objects are the pairs of topological spaces, and there are morphisms between these pairs. So that we are going to define now. If calligraphic A is admissible in the sense that it a, it contains those pairs of topological spaces that fulfill those three conditions that I mentioned earlier. So if A is admissible, homology theory on this calligraphic A, this class A, consists of three functions. To be more precise, three types of functions. One, a function HP for each pair in the admissible class calligraphic A. Okay, so here is a pair, and under this function that is going to map to this guy HP of x comma A, where HP of x comma A is an abelian group. So if you are comfortable with the notions of category theory, then you think of it as a functor between the category that we are working on, the category of admissible pairs of topological spaces, where there are certain morphisms that I haven't defined yet. So I did not talk about the morphisms between the pairs of topological spaces in the category of admissible pairs. But there is so first of all, here we are introducing the functor between two categories. On one hand, I have the category of admissible pairs, and on other hand, I have the category of abelian groups. On one side, in the category of admissible pairs, there are certain morphisms that I'll define in the second part of this definition. And on the other side, I have the morphisms to be group homomorphisms between abelian groups. So these functor takes the objects from the first category of admissible pairs of topological spaces to abelian groups in the category of abelian groups, which are objects in the category of abelian groups. Okay. So so that's the first ingredient of the morphisms in the picture. Then we have a function that for each integer p assigns to each continuous map H between pairs. XA to YB, a group homomorphism okay, which we denote by this, right? H star at P is a group homomorphism between these two groups, HP of X comma A to HP of Y comma B. Okay, right? So this is the morphism in the category that we are working on. This is the category of admissible pairs of topological spaces, and H is a morphism there. So X comma A is an object there, Y comma B is another object, and H is a morphism between them. And H star at P is the corresponding group homomorphism in the category of abelian groups here. Okay, so it's a functor, right? So H star at P is the image of H under the action of that functor. Okay, now, so a few a remark about this function H here. H H is thought to be acting on something like X, right? Where H of X is in Y in general, and for all X in big X. So you don't think of H acting on a pair, rather an element of the topological space X or its subspace A. All right. So H is a function from X to Y. So now we are describing that morphism between two objects in the category of admissible class of pairs of spaces. Okay, H is a function from X, the topological space X, to the topological space Y, such that it is important. We want H of X to be contained in the topological space B for all X in the topological space X. By the continuity of this map H from the pair X comma A to the pair Y comma B, we mean the continuity of the map H of the map H between these two topological spaces X and Y. Okay, So this is the description of the morphism between two objects in the category we are working on. All right. So now there is a group homomorphism, a function for each integer p assigning to each pair x comma a in in the object of the category that we are considering. So to each pair x comma a, uh, we have this HP of x comma a in the category of abelian groups, we know, and um, there is this group homomorphism. So in A there is a group homomorphism del star at P between HP of x comma a and HP minus 1 of a. So these are two objects in the category of abelian groups, and there is a group homomorphism between them, which we denote by del star at P, or which we discussed earlier. So in that spirit, we can call it homology boundary homomorphism. Okay. So these are the three notions of three functions that will turn out to be useful in the setup that we are following. And here you see that we have introduced this function HP, which acts on pairs and gives us abelian groups in the category of abelian groups. But what does it mean? It is not acting on any pair, HP minus 1. It is acting on A. So here A denotes the pair A comma empty space. Okay, these functions are to satisfy the following axioms where all pairs of spaces are in the class A. Okay, which is the class of the objects of the category that we are working on. Okay, this is axiom 1. If I is the identity, the identity map between pairs of topological spaces, right? Then the corresponding induced group homomorphism I star at P in the category of abelian groups is just the identity group homomorphism, is the identity homomorphism for all P in the set of integers. Now the second axiom, it tells us that if you take two maps between pairs of topological spaces in the class calligraphic A in such a way that we can compose them. Okay, suppose so we are writing K composed with H. So in order to have that well defined, H has to be between two pairs like X comma Y to Y comma X comma A to Y comma B, and K has to be from this pair Y comma B to another pair Z comma C. Okay, so that we can compose K with H, and that will be a morphism between the pairs X comma A and Z comma C. Okay, this is K composed with H, and the second axiom tells us that the group homomorphism induced from this composed map in the category in our category, which is in dimension P, which we write as K composed with H star at P, right? And it has to be equal to the group homomorphism induced by K in dimension P composed with the group homomorphism induced by H in dimension P. This is the second axiom. Okay, so here this is defined in the usual way. This acting on a point X of this topological space X is defined as K of H of X for all X in the topological space big X. Okay, so this is the second axiom. Now the third axiom, which is axiom 3, tells us that if F is a map between two pairs X comma A and Y comma B, then the following diagram commutes. Diagram commutes. HP of X comma A is mapped to HP of Y comma B. This is the induced group homomorphism of this map F, which is a morphism between these two pairs in the category of admissible pairs of topological spaces, which we denote by F star at P. And we already know that there exists this homomorphism A delta star at P, and in order to emphasize that we are working in this pair X comma A, we attach this superscript to this boundary map, boundary homomorphism, and we get to HP minus 1 at A. We know that such a from our definition, we know that such a group homomorphism exists in the category of abelian groups. Okay, and now there is this map to HP minus 1B, which is the restriction of F to the subspace A, and the induced homomorphism of that map when restricted to A in dimension P. That takes HP minus 1A of A to HP minus 1 of B, and there is this boundary homomorphism del star at P attached to this pair Y comma B. Okay, and this diagram commutes. Okay, this was axiom 3. Then we have axiom 4, which is which is called exactness axiom, which gives us the long exact homology sequence. The sequence as follows. So dot 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 dot, and then we go to HP of A, and then from HP of A to HP of X, this group homomorphism is induced by the inclusion map of A into X, or A comma empty space into X comma empty space, and we know that it's a well-defined inclusion since A is a subspace of X. This is I star at P, and then from HP of X to HP of X comma A, this is induced from this inclusion map X comma empty space included into X comma A. Okay, so this is denoted by pi star at P, and then from there back here HP minus 1A, this is the map del star at P, this is for X comma A. So we can leave it. We don't need to mention X comma A here because we are just working with one pair, X comma A, and then goes on like that on the right forever. This is a long exact homology sequence. So here I is the ordinary inclusion, the canonical inclusion of the subspace A in the topological space X, or if you want to see it in terms of pairs, it's nothing but the inclusion of the pair A comma empty space into X comma empty. Okay, and pi is this inclusion. Okay, good. And a few words about inclusion maps. The relation between pairs x prime comma a prime and x comma a in the class calligraphic A, or in the class of objects of the category of admissible class of pairs of topological spaces, given by x prime comma a prime being contained in x in the pair x comma a, we mean x prime is contained in x and a prime is contained in a separately, right? And then the map I from the pair x prime comma a prime into x comma a is defined by I of x is equal to x for all x in the topological space x prime. Is the case, this inclusion, so this is equal to this in the case when x prime comma a prime is contained in the pair x comma a, and this map I in this case is called the inclusion map. Now we have this notion of inclusion map between pairs of topological spaces, right? Okay, so the notion of homotopic map between pairs. Okay, so let's discuss this notion of homotopic map between pairs, it will be required for the homotopy axiom. So two maps H and K between the pairs X comma A and Y comma B are said to be homotopic, which we write as H is homotopic to K if there is a map big F from the pair X cross I to comma A cross I to the pair Y comma B. Okay, so as I mentioned earlier, that whenever we are thinking of a map between pairs, we think of when we try to understand this map in terms of the action of the map on the arguments, we take the argument from one of the components of the pairs, right? So in this case, say this one. And so these two maps are said to be homotopic when f of x comma 0 in one extreme of this the unit interval, closed unit interval 0 to 1 is going to be equal to h of x, and on the other extreme is f of x minus x comma 1 here. Okay, the other extreme of the closed unit interval, there it's going to be equal to k of x for all x in big X. Right? So it's evident that A cross I is a subspace of X cross I. Okay. So this is the notion of homotopy between two maps of pairs of topological spaces in the admissible class. Now, axiom 5, which is known as homotopy axiom, tells us that if H and K are homotopic, then their induced group homomorphisms in all dimensions will agree with each other for all P. Okay, good. Now the sixth axiom, which is known as Excision Axiom, which generalizes our excision theorem discussed in lecture 3. It tells us that given the pair x comma a in the class A, let U in X be open such that we just can't take any open set from X. We have to take that open set from the topological space X such that its closure is contained in the interior of this subspace A. Okay, so we have to be careful in choosing such open sets. So first of all, we choose such an open set U, and then if this pair is admissible, X set minus U, comma A set minus U, if this guy is admissible, that is, if the pair x set minus u comma a set minus u belongs to the class calligraphic A, then the inclusion map I from the pair, the inclusion of this pair x set minus u comma a set minus u in the pair x comma a induces an isomorphism induces an isomorphism I star at P H P of x set minus u comma a set minus u into HP of x comma a. This is an isomorphism. It's guaranteed by excision axiom. All right. So this inclusion will induce this isomorphism. This is the excision axiom. All right. Good. Now, axiom 7, which is called the dimension axiom. Dimension axiom. If big P is a one-point space, then the pth homology group of big P is equal to 0 for all non-zero small p. So this is small p, this is big P, for all non-zero small p. Okay, and the zeroth homology group of this guy, big P, is isomorphic to the additive group of integers. Something needs to be clarified here. This is not the general case. In general, so we have written down it to be isomorphic to Z, and in general, so we have written down it to be Z following Moncrief, but in general, it could be any other group G called the coefficient group. This has a name, it's called a coefficient group. Okay, so for details, see page 17 by the book by Eilenberg and Steenrod. Okay, so this is the seventh axiom, which is known as dimension axiom. Now we are going to state axiom 8, which is called axiom of compact supports. Axiom 8, which is known as axiom of compact supports. If alpha p is an element in the pth homology group, right, HP of x comma a, then there is an admissible pair x0 comma a0 with both x0 and a0 being compact, with both x0 and a0 being compact, such that alpha P belongs to the image of the group homomorphism HP of x0 comma a0 to HP of x comma a induced by the inclusion map I from I is the inclusion map of which includes x, the pair x0 a0 in the pair x comma a. Right? So we want x0 to be contained in x, and we want a0 to be contained in a. Right? So such a pair x0 comma a0 with both x0 and a0 compact is called a compact pair. Is called a compact pair. Okay. Good. Now I need to give you the axioms for simplicial theory, but in order to do that, I need to construct a few ingredients, right? So that I can formulate the homology theory in the context of simplicial complexes, in the setting of simplicial complexes. Okay, so here it goes, the axioms for simplicial theory. So recall that when we were dealing with simplicial homology theory, we did not define homology groups for general topological spaces. They were defined for simplicial complexes, right? And we also defined relative homology groups for pairs of simplicial complexes where the latter component of the pair is a subcomplex of the former component of the pair, right? Something like this, HP of k comma k0. This is the relative homology group of the complex K mod K0, where K0 is a subcomplex of the simplicial complex K. But have we talked about something like this before, where X and Y are topological spaces with certain desired properties? We did not. We have not talked about that, right? So this is what I'm writing. We have not defined homology groups for topological spaces in general. Topological spaces in general. We did so only for simplicial complexes. Okay. Now, given a polyhedron X, what is a polyhedron? It's the underlying space of a given simplicial complex. So given a polyhedron, so suppose that we are given a topological space X that is the underlying space of some simplicial complexes. So that's what I'm writing. There are many different simplicial complexes whose polytopes or underlying space, whose polytopes or underlying spaces equal X. Okay, so given a polyhedron, you can find many simplicial complexes whose polytopes are given by this given by this topological space X. Okay, the homology groups of these simplicial complexes are isomorphic to one another. Okay, right. It follows from the topological invariance of homology groups, right? In a natural way, but they are, however, distinct. They are nevertheless distinct groups. So these homology groups are distinct, but they are isomorphic. Similarly, if H from the topological space X to the topological space Y is a continuous map where where this X is the underlying space of a simplicial complex K, and this Y is the underlying space of another simplicial complex L. Let me write it. For simplicial complexes K and L, we have defined an induced group homomorphism H star at P induced by this continuous map. H star at P from the group HP of K to the group HP of L. Okay. Now, of course, if we also have two other simplicial complexes, M and N, such that these a topological space X is equal to the underlying space of the simplicial complex M, and Y is equal to the topological space Y is equal to the underlying space of the simplicial complex N. These are for two simplicial complexes M and N that are, of course, distinct from K and L respectively. Okay, so if you find two distinct So if we point to such simplicial complexes M and N that are distinct from our earlier complexes T and L respectively, then we also have an induced homomorphism HP of M to HP of N that we also denote by the same map, the same notation that we also denote by H star at P. So we have come across such notational ambiguities before, right? So what is the way out of this difficulty, right? So let me describe the way out of this difficulty now, right? We have these two homomorphisms that we have earlier denoted by, by the same symbol, H star at P. So the way out of this difficulty is as follows. Given a polyhedron X, we can consider the class of all simplicial complexes that have X as their polytopes. We form a class, right? We form a class of simplicial complexes that have all the same underlying space given by the topological space X. And we can identify the homology groups of these simplicial complexes in the natural way, of these simplicial complexes in a natural way. The resulting homology groups can be called the homology groups of the polyhedron X. The resulting homology groups can be called the homology groups of the polyhedron X. Homology groups of the polyhedron X. Okay, so more generally, we can perform the same construction for any topological space that is homeomorphic to a given polyhedron X, that is homeomorphic to a given polyhedron X. Now, this motivates us to give the following definition of triangulation, right? So, let me now give you this important, very important definition of triangulation that will give us a very important category, the category of triangulable pairs of topological spaces. Definition of triangulation I think it's a good time to take a break. So while I come back in the second segment, I will first define this triangulation and then go on to define the homology group of a triangulable pair. Okay, thank you for attending this first segment of the sixth lecture.